All right, 3-1, polynomial functions. It's actually called graphing. We'll talk about a little bit of graphing, but we really want to get a good foundation for our vocabulary today. So a polynomial function is just going to be x squared, x cubed, x to the fourth, x to the fifth. It can go on and on and on, no fractions or decimals as the exponent. So we've talked about polynomial functions when we talked about lines, so linear functions. We've talked about some polynomials when we talked about quadratics. So x squared is a polynomial, and they can keep getting larger and larger. So one of the vocab words that we definitely want to know is, that I forgot to put on this list here, standard form of a polynomial. And standard form is when we go from highest exponent to lowest. And that means if there is a constant, just a number by itself, is the last one, is the lowest, because it's actually x to the 0 power. So in this first example, we want to put it in standard form first. That means the highest exponent, so the one with the x to the fourth, we're going to put first. So negative 3x to the fourth. Then the third to the third. There is no squared, but there is just an x, and it's positive, so I'll put a plus sign for a positive. And then plus 6. This is standard form. This is what you will most likely see as the equation that you will graph later on throughout this entire unit. So standard form is the most common form and how we want it to look. So once we get that, we can state what the leading coefficient is. And the leading coefficient is just the number in the very, very, very front when it is in standard form. So notice it had to be in standard form to answer that correctly, because if you had just looked at the problem that was typed, you might have said 2, and that would have been incorrect. All right, so the degree is the highest exponent. Okay, so in this example, our degree is 4 because 2 to the 4th power is the highest one there. How many terms do we have? Terms are separated by plus and minus signs. So 1, 2, 3, and what are we going to use this one? 4. So that in this problem, the number of terms is 4. Okay. So I challenge you to try that one and see if you can get it right. I'm going to save a little bit of time and keep on scrolling though. All right. So we can understand in behavioral polynomials. So there are 4. There are 4 types of polynomials that we could have. Okay. And we could have a polynomial, we've done this before, a line that goes up or down, correct? Any type of line. So don't, if you're writing this down as you should be in your notebook, Don't try to get like the perfect picture of me. Any line, up and down, okay? We could have, this one might be new, but you will see it often. It's got some humps in it, but it's still going from bottom to top or top to bottom. So notice that both of those lines that I just drew, they're going the same direction, just the middles look different. So same thing could be true if I did, let's add another hump to it. But my arrows are still going in the same direction. That's called end behavior. All of those end behaviors happen when I have an odd degree. Okay? It goes from down to up if the leading coefficient is positive. It goes down if the leading coefficient is negative. All right, so if that's odd, then that means this must be an even degree. Right? The plus and minus are still true. So if the leading coefficient is positive, this is what it looks like. If the leading coefficient is negative, this is what it looks like. So remember a quadratic, if it was positive out front, it pointed up. But if it was negative out front, it pointed down. Okay, we're going to talk about some that maybe go to the fourth power. If it goes to the fourth power, all it does is have a hump in the middle, but notice my arrows are still going in the same direction. Okay, and we won't really talk about them much, but I could even add another hump and make it to the sixth power. But the idea there is that no matter what, your end directions are going the same. So what we say is for the end behavior here, so I'm out of space. I should have left a little more space if you have more space to write. I'm going to label this one A, B, C, and D. So the end behavior there is as x goes to negative infinity, y goes to negative infinity because they're both going left and down. As x goes to infinity, y goes to infinity. Okay. For C, it's the opposite. So as y goes to negative infinity, or sorry, x goes to negative infinity, y goes to infinity. And as x goes to infinity, y goes to negative infinity. Okay. For B, as x goes to negative infinity, so as that graph is going left, it is going up. As the graph is going right, then we say x goes to infinity. Y is also going up, so we say to infinity. And the last one, as x is going left, y is going down, so down is going to be negative infinity. As x is going to positive infinity, or going right, y is also going down. So when we're talking about end behavior, the answers are always one of these four choices for polynomials. So to determine that, we only look at the first one. The leading coefficient there. It's an even power. And it's positive. So even and positive is B. So my answer is x goes to negative infinity. Y goes to infinity. And as x goes to infinity, y still goes to infinity. Because without even graphing this on Desmos, which you totally can graph this on Desmos, but without graphing it on Desmos, I know that it's going to look similar to one of the graphs in B. Okay, if I look at the next one, it's an odd power, and it's negative. So that matches C. as x goes to negative infinity, y goes to infinity. And as x goes to infinity, y goes to negative infinity. So without even graphing that one, I know that my graph is going to look similar to C. Okay. All right. What if we wanted to interpret? So, sorry, touched my laptop. All the things happen. All right. Our next one, it says, consider this polynomial function. At the end of the day, if you have access to Desmos, all you're going to do on this one is put it in Desmos and graph it and match the graph. Now, if you can imagine back in the day, before there was Desmos, before there was a graphing calculator, we could still come up with close guesses by plugging in numbers, plotting those points, and drawing a somewhat of an outline that way. So that's all this example is doing, is having you draw that. So if I were you, instead of spending all that time, we're just going to say graph on Desmos. I do, however, know that it is to the 5th power. The leading coefficient is positive, so I know that it could look something like that before I ever even graph it. Okay, knowing in your head kind of how the graph is going to look by the end of the day is will help your deep understanding of it later. So just making sure that you get that part is a good idea. Okay. All right. Let's look at the real world problem and be done with 3-1. Danielle is engineering a new brand of shoes. For X shoes sold in thousands, a profit of this function in dollars in tens of thousands will be earned. How much will be earned in profit for selling 1,000 shoes? So remember, X is shoes. So everywhere that there's an X, I'm going to plug in 1,000. Now, I would type this in my calculator because I don't want to do that much math mentally, but if you want to do mental math, great. I'm actually going to show you another way. All right, so I typed the function in, the negative 3x to the 4th plus 4x cubed minus 2x squared plus 5x plus 10. In my little settings gear here, I pressed the settings gear and hit table, and this popped up in my table. Now, notice it asks how much will be earned for selling 1,000 shoes, but recall that everything is in 10,000s. So 1,000 shoes is actually when x equals 1, because, so let's go back. Remember this coordinate, 1, 14, okay? It's not 1,000 that I want to enter here. It's actually 1 because the key word there is in thousands. So if I think about 1,000, it's actually just 1, okay? So the answer here is 1, 14. Now notice that the output is in 10,000. So that means I multiply the 14 by 10,000 to get my final answer. They make a profit of 140,000. All right, so to ask, what are the x and y intercepts? So let's look. X and y intercepts are 10 and 14. Or sorry, that's the top. And then negative and positive. Okay. One point what? 9. Okay. And then we had a max at 14.1 something. All right. What do they mean in these contexts? So remember, I don't have negative money, so this part doesn't really make sense. But when I have 0, what's my profit if I have more than that and less than that. So if my x-intercepts are negative 0.86 and 1.9, this one does not make sense because it's a negative numbers and I can't have a negative amount of shoes sold. The 1.9 is fine because that's going to make sense, and it says that my cost will equal revenue if I make 1,900 pairs. So sometimes if you make too many of something, it is not worth the revenue. The y-intercept is 10. This means if there are no shoes sold, the profit is $100,000. But this does not make sense because profit cannot be earned when there is no product being sold. So x-intercepts are okay. Y-intercept does not make sense. Okay. Now, there are a lot of your coding and companies and workbooks that other people work with will, they have to use functions like this to find their profit and to find their cost in their business. So polynomials are also real world capable. The good news now is technology will do a lot of the work for you, but there still has to be someone out there to create that technology that works for you. All right, so you are finished with 3-1. I will be quiet so that you can work on your target.